the biggest, hairiest problems that exist as far as performance goes. Can you tell us a little bit about, first off with Joe, can you tell us a little bit about like your trajectory here at Databricks, like what you've been working on and some of the problems that you've seen out there?
Yeah, so we'll start with a bit of the trajectory. So I started at Databricks 3.5 years ago in like May of 2017 already. I think it's 2017. Coming in, I was relatively good at Spark, or so I thought. So I joined the experts at Databricks so I could get better at it. And little did I know, the engineers that wrote Spark are really, really good at Spark. And there's a lot of people that don't know a lot about Spark. So my career started as a solutions architect, working with some of the smaller customers, but I always got to run into really interesting issues. So issues like, small files, big files, things with Spill, things with Spark having bad plans, things with hardware, things with network. And I got to run into a whole bunch of little issues and work with some of these really good engineers. And that's kind of really how I went from just being someone that knew Spark pretty well to someone that can usually kind of dive in and pinpoint where your problem is and how to fix it pretty quickly. Over the course of the years, I've worked with people that have, with Reynold, our CTO, with people that worked on Catalyst Optimizer, the team that's building Delta Engine, the team that built Delta. So I've got to work with a lot of different people and pick up little, tips and tricks or things they notice, I try and remember. And that was kind of the trajectory. As far as like hairiest issues go, I've been in like quite a few where or I shouldn't say quite a few, but they all have a common starting point. And that common starting point is people will go to Stack Overflow, they'll watch Spark session talks, they will go to Google Groups, they'll go to the Spark Apache user group, they will go everywhere and they will find configurations that they think will make their job faster, and they have no idea what they do. And the hairiest problems always start there when you have a laundry list of configurations of which you know what to do. 2 configurations. So a really good example is Facebook put out a talk at Spark Summit like 2 or 3 years ago, and it was scaling Spark 2.2, I think was the version at the time, to petabyte or terabyte size. And I forget if it was like 68 terabytes or petabytes that Facebook was tuning their workload for. But I had a customer come in with a workload with, it was like 680 gigabytes. So they took all of the stuff from the Facebook page and they put it into their job. And they were wondering why it was running slow. So that one was really hairy in the sense I was like, did you just over-tune this and you have everything perfect? Or do you kind of not really know why you did what you did? You just did the route of, every person that's new to a technology does, go through Stack Overflow, go through the user groups, find things that work for other people and hope it works for you. So for that one, we just literally removed everything and it ran like 3 times faster. So that was the hairiest one.
So taking away sometimes actually gets you better than adding stuff in.
Yeah.
That's interesting.
It's like cooking, right? When there's too many recipes, they all overpower each other, and you end up with this thing that looks like, this brown liquid with some really burnt meat or something. Okay. So by doing less, you do more.
I feel offended. You just described my cooking skills.
Denny, you need to do less or do more with less.
Got it. Okay, my bad.
Hey, Chris. So how is this? Same question yourself, trajectory, how you started, how you got here, and kind of the biggest monster that you tackled or something like that.
Totally. Yeah, so I became like a junior data scientist at my last company I joined, and I originally thought I wanted to build really fancy models and predict things. I thought that would be really cool. And then I started actually doing it as a job, and I found I didn't like making models that were really bad all the time. And that felt bad to make models that were predicting things wrong all the time. And then I found out what I really enjoy is like building the source of truth. So like actually building and maintaining the data pipelines that analysts and data scientists will then rely on that data, being able to guarantee some amount of quality out of it, and ensuring that the pipelines are up and running all the time. And so then I was kind of managing data pipelines for a couple of years at this startup. And then we were a customer of Databricks. And so I got to kind of watch the company evolve, and I was using the product. And then our startup wasn't succeeding the way it was imagined. And so I got laid off, and that freed me up to come to Databricks. So I just emailed my SA rep, and I was like, hey, is there an opening here? And so I joined Databricks a couple of years ago.
Wow.
And then
That's an awesome story.
it lucked out really well for me, definitely. You know, some things are actually blessings in disguise. And then here, when I joined, we immediately started working with one of our healthcare customers, and I got put on a fairly long project with them, maybe 8 or 10 months. And that was where I kind of I had come from an ad tech background, so I had no domain knowledge anymore coming into this project, and kind of realized that when you're coming in as a Spark data engineer, it almost doesn't matter what the domain is, because data is just data. And at the end of the day, like what you are doing to data isn't actually that complicated. There's only so many things you can do to data. You can group it in different ways. You can, you know, collect it into different data formats. You can, but there's not actually, you know, at a high level, it's fairly generic. You have some data, you want to make it look different. And then you want to use that data to tell a story. And it's the story that actually matters, much more so than how you got to massaging the data into the format you needed to. So I got to spend a bunch of time kind of working at terabyte scales data lakes, and have a few stories. I think my personal favorite is HDFS. The way HDFS works is that there's a name node, which is kind of the central entry point to your overall storage layer. And if you have too much data in the HDFS portion, the name nodes will start crashing. So I've taken down quite a few name nodes with Delta Lake.
That's awesome. So which SA do I have to thank for bringing you on?
Vita was my essay.
Nice, very nice. That's awesome. So it's kind of like thinking about performance issues. I'm going to be pulling up a notebook here, and kind of how I want to center the next set of questions around is we talk a little bit about Delta Lake. While I'm pulling it up, I would love to hear some stories. I know, Chris, you were very close I think you were very close in the initial build out of Delta Lake. Is that correct?
Yeah. I got to work with the early customer of Delta Lake, and for the most part, we really had to kind of sit with them side by side, because they would take the newest build of Delta Lake and then immediately run it at a scale kind of 10 or 100x what most customers were running at, and would almost immediately find something to break. So over the course of a few months, they kind of helped us very rapidly scale up to being able to handle hundreds of terabytes per day. But while we were actually going through it, it was kind of like, okay, let's try this. Oh, that's broken now. This works at this scale. When we 10x, it doesn't work now. So kind of just taking things and then 10xing them and finding out that they don't work quite as well at 10x the scale. And then, you know, the way Databricks works is that we get handed a problem like that, and then we make it work at that scale.
That's awesome. So when we're talking about Spark and Delta, they kind of work together, right? So Spark, you can view it as like the computation engine, and then Delta is like the file format, the APIs around managing structured data on object store. The open source version works on HDFS, but Databricks version works on the cloud providers that we're on today. So when we're thinking about these concepts working together, oftentimes we have performance issues. So where do you start when you have a query that's not performing very well? So I have a query in here, and let's just say I'm bringing in my data, and I don't think it's performing the way that I think it should be. So I might have a select statement in here for a SQL query. Where do I start? Like, where do I go inside of Databricks to kind of tune the performance? Like, where would you start going?
Yeah, it's a great question. And I mean, I personally think Joe is even better at this than me. I always start with the Stages tab of the Spark UI. For me, the Stages tab is where you get the most amount of information in a quick way. You get the summary of each stage, you get the duration that it's taking, and you also get to see the amount of data that's processing. So if you expand the completed stages, yeah. So here, right, you get to see the duration of each stage, how many tasks there were, and then inputs, outputs, and shuffle file sizes. So this is where you can start to see, and this is where you kind of develop your intuition a little bit and say, okay, based on the amount of input data that we had and the number of tasks that we had, is that a slow stage, or is that a fast stage, or a normal stage? Is that the one we should be looking at in depth?
Interesting. So if something's got a lot of shuffle, is that a bad thing?
Not necessarily, right? I think shuffle is slow, definitely, and just for anybody out there who's wondering, shuffling is when you need to exchange data across executors, right? So we have a cluster of machines, and there are some operations where we're required to send data out across the network and exchange data across machines. And so this might be when you're aggregating data. Each executor is going to do local partial aggregation if possible, but then it's going to eventually need to send all the results to a single machine to get you that final answer. And so shuffle is required. It's not bad necessarily, but we should always be thinking that shuffle requires network transfer, and network transfer is always going to be slower than processing the data locally on the same machine.
Interesting. So shuffle's not all that bad. It's required sometimes, but if you're trying to tune for performance and there's a lot of shuffle going on, like where would you go to kind of start to analyze, well, is this a bad thing? Like, do I have too much shuffle, and where would I go about starting to fix it?
Right. Yeah, that's a great question. And so that's where, like, one thing then I start to think about is most people will scale out their clusters by just adding more nodes. But when you just add more nodes, AWS or Azure, like any of the clouds behind the scenes, those nodes are virtual nodes, and some of them might actually end up physically on the same machine. But if instead of adding just more nodes, if you switch over to larger nodes, and instead of just adding 8 times more nodes, if you switch to the 8x larger nodes, that's where you can start to see more local operations. So now you have more cores that are located on the same executor. And so if these tasks need to shuffle data, they don't necessarily have to shuffle it from one executor to another. They can do a local shuffle.
So if you have more cores on the box, that means they'll have more locality on the cluster, meaning that if there is shuffle, it's shuffling on the same machine, which doesn't have to go over the network.
Exactly. And maybe it helps to explain the mechanics of the shuffle. The way a shuffle works is there's what's called the map side of the shuffle, and then the reduce side of the shuffle. And so on the map side, each executor will write out the data that it has partially aggregated, or if you're joining, partially keyed, and it will write that data out to the local disk of the executor as shuffle files. And then on the reduce side of the executor, executors will start reading those shuffle files and pulling them across the network. And so if you have larger executors, each core is going to be reading shuffle files. So more cores reading from their own local disk instead of reading from a different node's local disk.
Interesting. So does it work? So Joe, I know that we're talking bigger nodes here, but on the flip side, I know that we've actually seen the other side of this actually show better performance where, you know, maybe not as large nodes, but not small, not like really small nodes either. I know we have a couple theories around this. You want to talk about that a little?
Yeah, so I don't want to go directly into that theory because if it's wrong, I don't want to look dumb. But basically what we've found is when you think about it, what Chris says makes sense. Like if you could have 10 machines with 10 cores or one machine with 100 cores, well, there's no network that needs to move because everything's on the same machine. And in theory, that all makes sense. But in practice, what we tend to see is actually the medium-sized machines do best. So on your screen there, you have the i3XL, 2XL, 4XL, 8XL. And what we tend to see is the 2X and the 4X outperform the XL, 8X, and 16X with all things else being equal. There's a couple theories with how the different cache like the L1, L2, L3 caches interact with the cores and doing cross-core cache reads. You know, there's a few theories for why that is. But generally what we see is the 2X and the 4X are the best machines to use. I'm sure that's, you know, not going to cover every edge case, but mostly that's the case. And one thing I would just kind of add to Chris's comment, shuffle is shuffle. There's a lot of times you can't get around it, but what you can do is look for strategies to reduce it. And the way you can reduce it is by doing more broadcast joins, by reordering your joins. So you join the smaller tables first, and then the bigger table, the bigger table, the bigger table. And the whole goal is just kind of think about how can we move the least amount of data. So if you join the two smallest tables to the next smallest table, that table's slowly getting bigger. But if you think about it, if you join the biggest table to the biggest table, you have to propagate that entire data set down your DAG. So thinking about your join order and using broadcast joins are really the only way to reduce that number without using bigger machine types.
Interesting. So what you're, if I can kind of synthesize a lot of the information that we just got, essentially what we're saying is that when we're talking about cluster sizing, really we're still figuring out we're still experimenting with different sizes, and it all depends kind of on your data volumes and what you're doing. This is my theory. I think that I think you're on point. I think that it's data volumes and then it's complexity of all the transformations. So are these compute heavy? Are they IO heavy? Like there's a lot of data coming in and out. Is it processor heavy? So is it compute, like are we compute strained? Some things that I've heard in the recent past is like, where are we constrained? Is it compute? Is it CPU side? Is it memory side? Is it network? Are we IO bound? Like where is the bottleneck? Where would you, so I know I have like mine, but where would you go to kind of, if you could just see like a big picture of where to quickly spot where we could be bound? Yeah,
I just actually did this for a customer on the other side of the world here. Go to your metrics tab and open your Ganglia UI.
Ganglia, what's that?
Yeah, so this is going to tell us what our cluster is doing. You have a very underutilized cluster, so it's going to be hard to exactly show. But basically, you can see almost all of this from right here. So the first part we usually look at is IO bound. So IO bounds when you're reading as fast as you can from your storage system. So what you'll see is on the right there, you'll see your cluster network level. Those numbers aren't always perfect. I believe they're at like 1 minute intervals. But if you're getting 40 megabytes per second per core on the read, that's about as fast as you can read in data. If it's highly compressed, then you're going to be CPU bound, but if it's not really highly compressed, you're just going to be network bound. IOs typically, well, they only happen on reads and writes. It's pretty intuitive. So that's kind of the first IO bound. The next part here is CPU bound. It's pretty obvious that one you're circling right there. You'll basically max it out around 80 or 90%. It's pretty common to be CPU bound when you're decompressing large Parquet files, large gzip files, anything that's compressed. Some operations are more CPU intensive than others. It'll be very apparent because you'll be using like 90 or 95% of your cluster, and that's what I would consider CPU bound. Memory bound is a little bit tougher to diagnose. So there's memory being used by the cache and by your JVM and your different regions in your JVM. And this tells you approximately how much you're using. So if Franco, if you were memory bound, or if we thought memory might be an issue, you would see this basically, the blue and green would actually go up to that 600 GB. And that's kind of an indicator, but the bigger place to look is when you're memory bound, you start spilling to disk. So if you go to your Spark UI and you go to your stages tab and just click on the longest running stage. This is typically how I do it. Come here, click on the description, yep. And what you'll see is under that shuffle right, you'll see a memory spill and a disk spill. And when you start to see that, that means you're kind of bounded by memory. That's one place to look at it. And then if you go to your SQL tab and just sort on the longest duration again, hopefully you did a join or something. Hopefully. So if you click on there, this will open up a UI and go ahead and expand the details. Scroll down to your hash aggregate. So in the hash aggregate, you'll see a spill size. If that's non-zero, that means that operation was probably memory bound.
Got it. So so Spark is in a little bit of background here. Spark is in memory cluster compute, right? So everything goes to memory to compute because it's faster, right, than going back to disk. So if the memory is, if you're out of memory, so if you've exhausted all the memory on the box, then it will then go to the disk. So it'll write the data to the disk instead of the memory because there's no more memory. So essentially spill means that your memory is full and now it's spilling over to the disk. So spilling to disk costs you time, right? Because disk is much slower than memory. So we want to reduce the amount of spill. What are some strategies to reduce the amount of spill?
Yeah, there's two. One's a lot better than the other. The first one is to increase your shuffle partitions, which are used in your joins and your aggregations. That's just a config Spark SQL shuffle partitions. You can safely increase it to about 20,000. Beyond that, then you have to start looking at that Facebook paper. The other way to do it, which is completely unintuitive, is you can decrease the core to RAM ratio by either increasing from a C4 to an I3 in the case of AWS, or by actually literally telling Spark to use less cores.
That's a config, right?
Yes, that's a config. I would generally never recommend reducing the cores unless you really know what you're doing. I guess, for example, that customer I'm working with on the other side of the world, we were running on DS15s on Azure. It has 20 cores, and we were seeing some spill, and we'd already moved our SQL partitions to 20,000. But by going from 20 cores to 18 cores, we were able to actually get the runtime from basically an hour to 54 minutes, and they wanted to break an hour. So it wasn't intuitive, but those are the two ways to do it.
I'm just Oh, sorry, Joe. I was just curious. Was it partially because maybe it had to cross sockets as well? Maybe the fact that it was actually dealing with the cache and when you're going between you have too many cores on that particular machine. Perhaps that was coming into play. At least it used to happen to me all the time in the past, but I don't know if that's in play any longer.
Yeah, so that's part of our long-standing kind of theory about how the really big machines with aggregations don't work really well. Spark is what we call node aware, but it's not like core or cache aware. So when you have like one core reaching into another core's L2 cache, you get the data, then you slow down, right? It's a theory.
Well, no. Actually, the theory is valid because that's exactly what we happened with. Now I'm really aging myself, but what happened back in SQL Server, we definitely noticed that when we were trying to with SQL Server, because it was going across the cross bridges between the sockets, right? What ended up happening is that because they actually hit the cross bridges, massive drop in performance. So we actually had to allocate memory to specific cores in order to be able to prevent the hitting the L2 and L3 caches, just like you're talking about. So I'm wondering if we're literally running into the same problem all over again now.
Yeah, you were assigning like resource groups with the.
Oh yeah, we were big time doing it, dude. It was ugly. It was ugly.
Yeah, it's non-uniform memory access is what you were messing with, right?
That's right. Oh yeah, NUMA. There we go. See, I forget. That's exactly. It's all about NUMA, baby. That's right. That's right.
Yeah.
That's awesome. So
no, actually, it is.
I mean, it's awesome that it's the same problems, right? Because I remember NUMA nodes was a big kind of, Denny, that's probably what you're talking about, right? SQL Server.
Absolutely. Yeah. We were mucking around with it, trying to reconfigure the assignment groups. Any large systems, basically, what we realized that even before we had the problem of like when we're doing sharding, that's exactly it. That we were in essence sharding within the same machine because they became large enough where basically the NUMA non-uniform memory allocation just actually had a massively large impact in performance.
That's awesome. So kind of just to talk about the memory to core calculation that you were talking about, if we look here on the drop down, this is what you're talking about. There's 4 cores sharing 30.5 gigs of memory, and each instance type, whatever cloud you're on, right? Is this what you're talking about? Are we talking actually like the closer memory to the processor?
No, we're just talking about the core to RAM ratio of the machine.
So if you're having spill problems, you want to increase the ratio or decrease the ratio?
You want to increase the amount of RAM per core. So I don't know if you're doing cores to RAM or RAMs to core, but
sure. So then a memory optimized cluster, because you would have, if we take like example of 4 into 30, you would have, oh wait, but 8 into 15 would be less. So you would have more memory to core with this series where you have 4 cores sharing 30 gigs of memory.
Yeah. And I mean, for better or worse, we give you a ton of options, but at the end of the day, you should probably be using the C4 8X or the i3 4X for most workloads. There's going to be times where the general processing of like an M4 is fine. And I know we give you all of these options, but usually using the C5 8X, the C5 D9X, or the i3 4X is good enough. I mean, you can try everything you want, but at the end of the day, those 3 will probably be best. So don't get too hung up here.
Yeah, I agree. The one thing I want to say about choosing the right, a lot of times is choosing the right infrastructure for the right job. And I know, Fish, you've got some tips here based upon some things you've seen. And especially, I've actually done some testing here. I really like the C5Ds. C5Ds actually include locally attached fast disk, and you can enable Delta cache on these cluster types. So you gain the benefits of compute optimized along with the locally attached fast disk for Delta cache. So I saw really good performance here. But Chris, what have you seen out there? Like what would, if you had like recommendations, what would you say?
Yeah, definitely. I think both Joe and I have worked with a bunch of customers who have done some pretty serious testing of workloads. And I mean, if you're a data engineer, I think this is one of the most fun things that you get to do, perhaps fun in a boring way, but just getting to run a workload that you know the inputs and outputs, and you have a really solid baseline for how the job runs, and then getting to run that job on different instance types and seeing how it affects it. The things that you know you guys have been talking about this whole time are going to come into play there, where you're thinking about things in terms of per core throughput, and thinking about things in terms of the memory to core ratio. And then like you were just showing, so the different instance types have different hardware under the hood. And so things like the C5 instances, right, are the compute optimized instances. What that means is that these instances have a really low memory to core ratio. They only have 2 gigabytes of memory per core. So if there are certain Spark operations require a lot of memory. Typically it's joins and aggregations require a lot of memory, where each key that you are joining on or aggregating on requires a certain amount of memory. But if you're just doing flat transformations, like just parsing strings or doing simple transformations like that, then you don't really need that much memory per core. And so these C5 instances are the cheapest core pricing in AWS. And so here you can basically get a huge number of cores at a really cheap per core price. And as Joe was describing, you are basically getting throughput on a per core basis. So cores become really cheap here, and you can easily scale out your job by just adding more cores and increasing the throughput that you can get, both on the read side. If you're reading from Kinesis or Kafka, adding more cores means you can pull more data. And on the write side, you're going to get bottlenecked at a per core throughput level to S3 or something like that. And so adding more cores gives you an easy way to scale that out. And these C5s have the fastest processors under the hood. And I think, you know, we've been able to benchmark single cores of these at being able to process hundreds of thousands of records per second.
Wow.
One thing. Oh, sorry,
yeah,
Chris, go ahead.
No,
I was about to ask you that question, because it looks like C5s are also using non-volatile memory as their local storage, right? And so it seems to me then so I think there's an implication of basically, even though Spark, if it does spill the disk, has a tendency to be to random IOPS, right? Because it's SSDs, I wouldn't say it doesn't matter, but the performance is not that nearly as slow just because it is on SSDs. So I just wanted to add that fact. Sorry.
Right. Yeah, exactly. Or if you're reading Delta tables, we'll be able to cache it on the local disk, as Franco mentioned.
Yeah, they're called these types of VMs where you have the locally attached NVMEs. I call them forgiving instances, because if you spill the disk, it's forgiving because the job will still finish if you have to spill.
Yeah, it still takes the same time to write. It's just the reads are way faster.
Interesting.
And then the other thing I want to point out while we're here actually is the network bandwidth column.
Yeah.
So this is something a lot of people don't realize, but you know, under the hood, right? These are all virtual machines. So when you request a C5 X large, they're giving you 1/24th of a C5 24X large. Like a C5 24X large is the actual whole machine in a server rack. And so when you request a slice of that virtual machine, you're also only given a slice of the overall network bandwidth that the rack can support. So the rack itself has 25 gigabits of bandwidth. But when you request the smaller instance types, you're getting a fraction of that. And what you can see is that as you go up the instance sizing, there is a breakpoint where you're actually guaranteed now a certain amount of bandwidth. And so here the breakpoint for me is the 9x larges, because under that, you're only guaranteed up to 10 gigabits per second, and they will throttle your bandwidth if there are other machines on that same rack using a lot of bandwidth. But if you go up to the 9x larges, you're now guaranteed a static 10 gigabits per second as the minimum throughput that you're going to get. And so if you have these workloads, like as Joe was mentioning, most ETL workloads are actually network bandwidth, network bottleneck. And so by moving up to these larger instance types where you're now guaranteed a certain amount of throughput, you can actually end up getting better writes going through to especially to S3.
That's great, and that's exactly what I wanted to get to by showing these. So thank you for pointing that out. So when we were talking about being network bound or being memory bound, and we had kind of the core to memory, conversation. So when we're talking about being network bound or being compute bound, so there's multiple ways. It's not just configuring Spark. Sometimes we need to think about the virtualized infrastructure that we're spinning up in the cloud underneath the covers. And Chris pointed out a very good point. There is this big difference between up to 10 gigabits per second and 10 gigabits per second, especially when you could be reading and writing a lot of data to and from object store like S3, or if you're on another cloud provider. It's a very similar concept from cloud to cloud. Like Chris mentioned, you have a very large rack, right? And then they virtualize the servers, and they slice everything up, right? So get up to 10, you're basically sharing hardware, right, with other people. So you're sharing the NIC, the network card. Whereas if you move up, you kind of get guaranteed. And as you see, if you go up even further, you get guaranteed 25 gigabits per second. And I know that there are some exotic, correct me if I'm wrong, are there more exotic types that actually have multiple NICs? Or am I confusing something?
No, I think some of the newest instance types, Amazon is starting to build, their own hardware accelerators on top of these server racks. So I think there definitely is. But those kinds of things are usually, you have to think about the hierarchy of needs in the cloud. Like those things are first usually targeted for web-facing stuff, right? So like web-facing stuff still has the highest network needs, but definitely sort of as S3 become, and object storage in general, like you said, this is not unique to AWS. Azure has these same details for their VMs. As more and more people are using object storage for analytics, right? The network throughput of the object storage becomes more and more obvious to the users. And so I think the clouds are very much working on this to accelerate these speeds inside their data centers and across data centers. So that's kind of the important bit too, right? Is this is going to apply sort of across a region with many data centers, and they want to provide the best experience to their users.
Yeah, there's a similar, I can't, I'm not finding it here, but there's a similar chart on the Azure side where it's a very similar experience where you have different compute sizes and then they kind of go up. Here it is. This is the BS series, and it's the same concept, right? You've got, it doesn't look like they have a NIC on here. But
there's another, there's another version of this page, I think, without the pricing that has the network throughput.
Got it. So it's the same concept. So, when you're out there diagnosing performance, it's not just Spark that you take a look at. I know that as a newcomer, I've only dabbled with Cloud Databricks, Cloud Spark, but on-prem, I know that some of the differences when I kind of talk to people that might have their own Spark and Delta instances, that they have to deal with stuff on the Spark side because you're sharing one big machine and you're slicing up Spark to all these different use cases or applications. Whereas in the cloud, you're going to spin up that instance and it's going to be that cluster, right? And it's going to be your instances. So it's kind of like this thought process change that happens in the cloud. So I just wanted to spend a little bit of time talking about virtualized hardware when we're talking about kind of diagnosing performance problems. So when you're in Ganglia and you kind of can see that you're bound by one of these three, right? You're either going to have memory, CPU, or network. There's more than one way to kind of dissect and understand and solve that problem. Spark configs is one thing, but there's only so much you can do there. right? Let's take a look at the virtualized hardware under the covers. Let's take a look at what resources I have available. And sometimes choosing a different instance type will get you better performance. And in the cloud, if you pay for infrastructure over time, and if you boot a C5D12XL and it finishes in, let's say, a fourth of the time that a C5D2XL does, and it's a little bit more pricey, you could actually be cheaper by going to the bigger instance type. Have you all ever seen anything like that in the wild?
All the time.
Really? Wow. So it's something good to take a look at if you're analyzing your performance.
Yeah, I actually just had this happen. I just went through this with the customer where they switched from the C5 2Xs to the C5 9Xs, and they were super network bound, and they immediately got a speed up, a pretty significant speed up.
That is amazing.
Yeah, I did
And
it.
I think,
And we went from a D series or an E series to a D series on Azure. Job ran twice as fast.
Wow. So it's something to pay attention to when you're out there diagnosing. Denny, do we have the time check?
Yeah, we probably have about four to 5 more minutes, so we can probably go a little bit more before we do it. But I did want to call out, actually, we did have some questions from the audience, specifically around like which instance types do you want to use for ETL versus machine learning versus aggregate, and I was basically sort of answering the questions on live, basically saying the answer is always it depends, right? I mean, because the reality is, your ETL process may be streaming related. So then yes, it's perfectly fine to be more core / memory heavy versus maybe aggregate heavy. Well, then maybe you don't want so many different nodes, right? So that way you can reduce shuffling and so forth and so forth. And even what I just said isn't necessarily correct, right? I'm more than sure Joe and Chris and everybody else for that matter can pull up an example where what I just said is wrong. Okay, so it's back to good old-fashioned testing. And so I don't know if you guys want to add anything else to it, but I did want to sort of overemphasize that point, because while there may be some rules of thumbs that we can begin with, it's certainly not the finishing point.
Yeah, I think it goes back to identifying where you're bound and then solving for your boundary, right? So if you know you're memory bound, you're seeing spill in your joins, well, you probably want to go from a C to an I or a C to an R, or from a F to a L in Azure. So I hate saying it depends, and I like to be prescriptive. It depends makes things seem like they're more complex than they are. So I guess Franco's kind of trying to show you like the thought process behind how we do it. So, I mean, in my head, it's kind of like a science at this point. Like I do A, B, C, and then I try this. And then if I need to do better, I do, X, Y, Z, and then I try this. And it's always the same few steps. It's just where you start slightly different.
That's great. That's the hardest part for someone like me who was learning the stuff on the fly a couple of years ago. The hardest part is like, where do I start, right? And I think we've given some really good tips today on where to start. I had a bunch of other questions. I think we covered some great stuff today. Denny, do we want to take is there another good question that we got on the queue out in the wild that maybe we want to take, or should I ask one of mine?
No, ask one of yours, because in fact, actually, we literally, with that one question, we basically summarized most of the questions, basically.
Awesome. Whew, I kind of asked that one. Let's go with what has been some of the largest data volumes or complexity that you've solved in the wild? Could be, I could think of one story that I found humorous on Joe's side with that that one time. But we'll take it one at a time. Chris and or Joe, who wants to go first? One crazy story about an insanely large or insanely complex and how you solved it.
Go for it, Chris.
Okay, yeah. I think I'll retell the name node story. We had this POC going on where we wanted to do a bake-off on an 80 terabyte data set. and a bake-off between a couple different data formats and a couple different engines. And at 80 terabytes, it's actually, as you might imagine, it's pretty slow to actually alter the data format. And so this was kind of one of those things that really just made it obvious how much Delta has changed the way we deal with data engineering. Like one of the formats being baked off was ORC and high VASID tables. And so ETLing the data into that format took several days. And when there were failures, you had to go in and do a lot of manual cleanup. There was just basically a ton of manual work. And then to get it into Delta Lake, I just streamed it in and set auto optimize and optimized writes on, and just kind of left it alone for 6 hours, and then it was done. And there may have been some intermittent failures in the middle of it, but the stream just recovered and restarted. And Delta, because it automatically deals with those, we never had to worry about it on the read side. Just kind of left things alone. It was like one of those things where, and then there was a third one of just straight Parquet. That one was a massive headache that I won't go into. Just kind of highlighting the differences between the formats and just how easy Delta kind of makes things these days.
That's awesome. Joe?
I'll be brief. So one of the bigger ones I've worked on recently was a daily ETL job that was joining like, I don't know, 55, 60 terabytes of data to 20 other tables. And we ran into issues not really related to Spark, but just like running Spark at that scale in the cloud. So things like the different, like S3 goes on AWS. So S3 throttled us pretty good. Requesting a cluster that big was a little kind of shaky. Using spot instances, we flooded the spot market. So that one was probably one of the bigger ones, and it led, I mean, that's kind of how we know some of these hardware things is when you get to a certain size, like it's not Spark that's the problem, it's the hardware and the cloud and everything else that goes and interacts with it. So that was probably one of the bigger headaches, but more fun ones and things I learned a lot from.
That's awesome. I just want to touch on a couple of things. When Chris was talking about the fault tolerance of Delta in streaming, just to provide a little bit of color there, the structured streaming has the checkpoint directory, which keeps track of everything, of all the files that it's ingesting. Delta has the transaction log. These two things work together. So if something happens midstream, fails, the new cluster can boot up and figure out where the heck it landed, and it basically picks up from where it left off and it continues processing. Did I repeat that correctly? That's amazing. I'll tell you some tricks I've done in the field with knowing those things. You can inject more nodes into a cluster midstream to get things to run faster. So because state and transaction log stuff is managed, you can do really interesting things, right? And if there's a failure, it's no big deal. You just restart the stream. Spark and Delta kind of pick up the pieces and pick up where it left off and keeps going. All right, with that, are we clear to close?
We are. So this is perfect timing. I was just about to ask, let me shift over. So let me go ahead and share my screen. While we're doing that, boom. Okay, give me a second here. All right, so hopefully you guys are able to see my screen. So for starters, I want to say thank you very much to Fish and Joe for this awesome session with Franco and myself. Really good info, like always. For those of you wondering, the notebook that Franco was playing with, as well as this recording, both on LinkedIn Live and YouTube. Well, they're already on LinkedIn Live and YouTube, so you have the recordings. The notebooks we'll put in github.com/Databricks/Tech Talks. It's the usual location for these series, so that way you can go play with the notebook as well. So again, thanks very much to these gentlemen. Let's go ahead. We want to do some quick call outs. For starters, for example, the Data and AI Summit, Europe. That's actually next week, okay? Next week in GMT time zones, formerly known as the Spark and AI Summit. So we have some awesome names. We have some really cool folks. In addition to Mae Jemison, who's this awesome former NASA astronaut, which of course blows to my heart. There's also Malcolm Gladwell, which he's amazing. If you get nothing from this, read Outliers, his book, and listen to his podcast, Revisionist History. Seriously good stuff. We have multiple meetups. We have AMA sessions, and we have training. There's a 25% off training here, DAIS 20 meetups. You use that, you get 25% off. So want to call that out. If you're interested in presenting, okay, submit your project for the Data and AI Summit Europe for Community Lightning Talks. They're going to actually happen in European time zone, so be aware of that fact. They will be live. They will be fast. Submit your project. Just go to Data and AI Summit Europe. You're going to be able to see the link there. Click on it. The first 10 to submit and their projects will receive also free VIP passes, which include exclusive AMAs on Delta and Photon, which, by the way, the gentlemen here on this on this call are going to also be on some of those AMA sessions as well. Okay. For the meetups, we have the Databricks University Alliance meetup. That's on the 17th with these fine people. We have Olivier Gerard from MBA ESG. We have Kyle Hamilton from UC Berkeley, and we have Linus Wallen from Yongkabing University. I apologize if I said that wrong. And of course, Rob Reed from Databricks, who's our University Alliance Manager. He will be there to go ahead and MC that session. Okay, so you want to know a little bit more about how to use Databricks in your university? Boom, this is the meetup to attend. We also have a Data and AI online meetup on Apache Spark 3.0 internals and building structured streaming microservices architectures with Scott Haynes from Twilio and Jacek Lazowski, who's an independent consultant, but writes the very popular Spark internals ebook. Okay. It'll be hosted by Jules and myself. So that'll be on Wednesday. And then on the following day, we'll actually have another Data and AI online meetup for MLflow, Delta Lake, and Lakehouse use cases. So with Andre Masarevic and Oliver Koenig from Databricks on MLflow and Lakehouse scenarios with Delta Lake, of course, and again, all hosted by Jules and myself. So as you can tell, lots of fun stuff next week. So and even though we've scheduled them primary for GMT times, for those in the US, because they're late enough GMT, they actually should be somewhat comfortable for those in the American time zones as well. Okay. And final little spiel, don't forget to check out Data Brew. This is a vidcast podcast series by myself and Brooke Winnick. Brooke is the real star of the show. We discuss with external panelists on data in the data and AI community on a lot of really cool topics. For example, the first session is with Barry Devlin, Susan O'Connell, and Donald Farmer. If you're familiar, you may be familiar with some of those names, especially for coming from the data warehousing world. From data warehousing to data lakes in about 40 minutes. It's actually more like 44, but whatever. So anyways, definitely check it out. Just go to databricks.com/discover/data-brew. You'll be able to hear the series. We actually will be pushing out podcasts about every 2 to 3 weeks. The next one actually will be with our CEO Ali Ghazdi. So perfectly good stuff and fun stuff to be listening to. Okay, and don't forget, also the third one will be with Michael Armbrust. So we get all geeky as well. So that's it for the spiel for today. Again, I wanted to thank Chris and Joe for their presenting their session. Franco, like always, for going ahead and running the show. This is awesome. Anything you guys want to toss in before we call it for today?
Yeah, I have a talk. If you liked this and you want more Delta and Spark performance tips, I'm actually doing a talk at Data and AI Summit this year. You should check it out.
Bam. Excellent. How about you, Fish or Joe?
I think I talked enough the last hour.
I disagree.
I completely disagree. Yes. All right. Well, I think that's it for today. Thank you very much, everybody, for attending today's session. We apologize for not necessarily being able to answer all questions, but we'll be online again like usual, and definitely look for us next week at Data and AI Summit. Our ugly mugs will be up there. Okay.
Bye, everybody.